Welcome everyone. This is New England Dynamics and Number Theory Seminar. It's our last meeting of spring 2024 semester. So before we escape to the winter break, let's hear Soffer Aranov, who will tell us about escape of mass of the sequences.
Okay. Hi, so thank you again very much for having me for the second time. It's an honor to be here. So I did promise this is escape of massive sequences, but let's first talk about continued fractions. So we all know that if you have a quadratic irrational theta, then you can write out its continued fraction expansion in this form, and it's periodic. That is, there is some part of it that will just repeat itself infinitely often if you have a quadratic irrational. So now we also know that if p is some prime number and theta is a quadratic irrational, then p theta is also going to be a quadratic irrational, and p squared theta and p to the k theta in general. So this raises the question of how does the continued fraction expansion of p to the k theta evolve as k goes to infinity? So let's try to formulate this in a more accurate way. So if you have some prime, let's now write this continued fraction expansion of p to the k theta in this form as bk0, bk1 up to bkmk. This is the initial part. And then you have the periodic part, which is ak1 up to aklk. So you can ask a few things. For example, what happens to the period? Does the period stay finite? Is it bounded? Or does it go to infinity? And at which rate? So as it turns out, one thing that we can see, and this is a theorem by Hecke and Shapira from 2017, is that the period is exponential. That is, the period of p to the k theta is of order of magnitude p to the k, and there's some small error term here as well. And then we can ask another question. So we know that the period is going to become very, very large. And we can ask, what about the elements in the periodic part of the continued fraction expansion? Do they also become very large? And as it turns out that they do, that is, the limit as k goes to infinity of the largest element here is going to be infinity. So I have two things that are very large. One is the length of the period, and the other one is the largest element that we see in the periodic part. So we can ask which one's larger. And as it turns out, the length of the period is going to be significantly larger in this sense. So moreover, what they showed is that there's no escape of mass here. This term is kind of funny in this setting, but later on we'll see how it relates. So what does this no escape of mass mean? This means that the limit as k goes to infinity of the maximal term here, the log of the maximal term, divided by the sum of the logarithms of all of these terms, is going to be 0. So these are some results here. Let's now discuss the idea of the proof. So for the idea of the proof is that they don't discuss continued fraction expansions. Rather, they utilize the connection between the Poincaré section in the upper half plane and the continued fraction expansion. And then they connect this to lattices in PGL2R mod PGL2Z. After doing this, they were able to talk about something else, which is instead of continued fractions, you forget about this completely. You just discuss the escape of mass of measures that are supported on compact nested diagonal orbits. I'll get more into this. So here's the setting. The setting here is that Rg is that we have this homogeneous space, which is G infinity mod gamma infinity, where G infinity is PGL2R and gamma infinity is PGL2Z. And we have the diagonal group in G infinity. And we are now going to define something called Hecke friends. That is, we say that two lattices in X infinity, they're Hecke neighbors if lambda 2 is contained in lambda 1, and lambda 1 mod lambda 2 is isomorphic to z mod pz. So this is like saying that they're p Hecke neighbors. And then they're Hecke friends if you could do the same thing, but now you have p to the k. And the idea is that we connect any two Hecke neighbors with an edge in some infinite tree, and this is how we create this Hecke tree. So what's the idea behind this? We have some base lattice lambda 0, and then we look at all of its Hecke friends that lie below it, and this is going to form a regular tree. And now it turns out that if lambda 0 has a compact diagonal orbit, then how does this go back to what we said earlier? Firstly, lambda 0 is going to correspond to some quadratic irrational. This is a well-known fact by Dirichlet's unit theorem. And not just that, all of its Hecke friends that lie below it are also going to correspond to some quadratic irrational that lies in Q theta. So now all of these are also going to support an A invariant probability measure. So instead of discussing quadratic irrationals, what they showed is that this is similar, or at least equivalent in some form, to discussing all of these measures along what happens to these measures and whether or not they have escape of mass. That is, whether these measures, they will converge to a probability measure, or whether they converge to something which gives full mass to x infinity, which is less than 1. So that's what they discussed in order to talk about this in terms of Hecke trees and not in terms of continued fraction expansions. So in this way, they just studied these measures and what happens to their limits when you take them along a branch in the tree. So now I said a lot of words. Let's see some pictures. So here's how this tree looks like. You take some lambda 0, and then you look at this tree. So these are the neighbors. So over here we have the Hecke neighbors, and then here's the Hecke neighbors of them, which are the friends, and so on and so forth. And then what happens is they want to study what happens to these measures if you vary them along branches in this tree, but not just any generic branch, rather a particular type of branch called a rational branch. That is a branch that at some point, it may zigzag, but at some point it must always go right. And the reason why it's called a rational branch is because it corresponds to a rational point on the boundary of the tree. So I drew this here a little bit, and this is a general picture of how this all looks like. So now let's discuss what were the results in terms of the Hecke trees. So we say that some probability measures, they exhibit C escape of mass if any accumulation point of them gives mass to the entire space x infinity of at most 1 minus C, where C is greater than 0. And full escape means that you can take C equals 1. That is, any accumulation point is the 0 measure. So the main result that they showed is that the escape of mass of these sequences here, p to the k theta, as of the continued fraction expansions, they correspond to the escape of mass of these probability measures, mu of A on these guys here. So recall that we had for every one of these compact diagonal orbits, we had a quadratic irrational that corresponds to it. In this case, you simply take this guy here, this p to the k theta, and then construct the lattice that corresponds to it, and look at its its measure here that corresponds to this compact diagonal orbit, and then you look at what happens to these guys. So, and what are their weak star accumulation points?
So this is a definition of escape of mass, yes, of P's powers.
Yeah.
Can you express it in an equivalent way, some kind of condition on coefficients?
Yes, that was what we showed earlier, actually. That was one of the previous slides. That this analysis, I'll show you in a bit here. So it was this guy here. So it was this thing here. So this thing here is this escape of mass.
Okay, so this is equivalent to saying that the measures don't escape.
Yes, indeed.
Okay.
So that's what they showed. And then they improved this through the Hecke trees. Sorry, I'm just getting back to where I was. Okay, So their main theorem is that if you take these rational branches, that is branches that are of this form where theta is some quadratic irrational, then they do not exhibit any escape of mass. And they also showed that these type of measures must equidistribute. So this was the main thing that they showed in this paper. And then the next step that they did was ask, is this true if I change the setting? This was a real setting. And they asked, what happens if you change this with function fields? So the results here are actually very surprising and not at all like the real case. And we're going to discuss this, but first we have to define what is the function field setting. So in this setting, our Laurent polynomials are going to be FQT with these brackets. That's going to be the sum of a n t to the n, where n goes over powers that are at least 0, and there's at most finitely many powers here. And the Laurent series are going to be these guys here. That is, it's the same thing, only you could have infinitely many negative powers, but at most finitely many positive powers. So now let's discuss continued fractions here. If you have some continued fraction, if you have some quadratic irrational or any number, then you could just write its continued fraction expansion in the same type of way that you would do in the real case, only now the elements in the continued fraction expansion, they're going to be polynomials. And in particular, some theta is going to be a quadratic irrational if and only if its continued fraction expansion is periodic. And then we can ask the exact same questions that we asked in the real case, which is, how does the continued fraction expansion of t to the k theta distribute? So you could take some general prime, let's say pt, where p is some prime or irreducible polynomial, but let's focus for simplicity just on t to the k theta. So let's see what results we know in this setting. In this setting, we're going to write out the continued fraction expansion of t to the k theta in this form. And now we have some known results. The first one is an old result by Mathan and Teullie, which says that the maximal degree that you see here is going to go to infinity as you take k going to infinity. And then another result is now about the length of the period. This is different than in the real setting, where we call that it was exponential. Here, Kaminsky, Paulin, and Shapira prove the length of the period is going to be polynomial in k. And this creates a setting where you have some escape of mass. That is, a result by Paulin and Shapira is that for every quadratic irrational, you can find some positive c such that you will always have escape of mass. And not just that, what they said is the following. If you look at, let me just talk about this expression here. So you take the maximal element that you see here, but then you ask, is it larger than some n? Choose an n that you want as large as you want, as possible. And then you look at what's this guy here. So take the distance of this guy from n and divide it by the sum of the degrees over here. And then you look at the lim-inf of this. So no matter which sequence that you'll take of these k's or these n's, you're always going to get, this is going to be larger than c. And this is called c escape of mass. So they found that for every quadratic irrational, you will always have c escape of mass, where c depends only on theta. And now let's discuss the idea of the proof. The idea was very similar to what was happening in the real setting, which is, again, we use these Hecke trees. That is, you define these lattices that they have, that they correspond to these nested that they correspond to these nested number fields. And then you study the escape of mass of the measures taken along these branches. But now, instead of being in PGL2R mod PGL2Z, they're in the natural analog, which is PGL2 Laurent series mod PGL2 Laurent polynomials. And in order to study this escape of mass, I'll go into a little more detail here. Then what they did was that they studied the evolution of the lengths of the shortest non-zero vectors in these type of lattices where you normalize them in some type of way. And where you take this flow. So this is the beauty of it, that the escape of mass, it corresponds to this length of the shortest vector. And this is, you could say, something from geometry of numbers, and somehow seems unrelated to the continued fraction expansions. And then what they did to connect this to the continued fraction expansions is that they used a paper by Paulin, which discusses the same type of connection between the upper half plane and the continued fraction expansions, but in this positive characteristic setting. So now let me just draw a picture of what happens. So here, this here is going to be what's called the full down property in the tree. So one of the things that you could do is say that you have some lattice. So maybe I'll write a little bit here. So say that you have some lattice lambda. And now you're going to look at, and this is going to be in the tree, a t to the at, that was what I had earlier, to the n lambda. And you look at the length of the shortest non-zero vector in here. So say that you started out with the vector being very, very short. This is going to be length 1, which is the longest possible length of the shortest non-zero vector that you have. And this is due to Minkowski's second theorem. So say that you start here, and say that at some point, maybe you make your vector, so when you apply A here, then you can either make the length of the shortest non-zero vector longer or shorter. So if you made it shorter, you're going to go this way, but then if you made it longer, you're going to go here. And one thing that happens that's pretty nice here is that once you make it longer, you can't do this. I made it a little bit longer and then I went shorter. You can't do that. That won't work. What you can do, what you have to do is at the minute that you make it longer, you have to make it long until it gets to length 1. And then after that, the length of the shortest vector in the lattice is going to change when you apply the flow one more time. And then you're going to shorten it and then keep on going in this manner. And then what happens is that one way to see this exponential versus polynomial growth is that in this case here, you're going to, so in the positive characteristic setting, the length of the period, as I said, was going to be linear. And this corresponds to the length of this period here, of the length of the flow under the period of this guy here under this flow. So since it's linear, say you got here and then you closed it, and then you would just repeat yourself by doing this action here, then what would happen is if I were to ask, choose something, and you ask, what does escape of mass correspond to? We know by Mahler's compactness criterion that this corresponds to having very, very short vectors. So you could say, okay, let me choose a line, this line here. And I will ask, what's the proportion of the period that's going to lie over here? And that would correspond to the amount of mass that escapes in the end when you do this, when you take some limit of this. So as you can see here, since this picture here is going to be linear, then you're going to have, then you can't have that all the mass is going to be right of this line or of any line that you choose, because you will always have to have some mass over here. But on the other hand, if you were to draw it exponentially, then you would have something like this. And then if you choose a line, then you could have that nearly all the mass would be here because this is exponential and this would win this tiny portion that you have here. So that's a more or less intuitive idea of this proof. And one more thing that they conjectured above this was that not only do you have some partial escape of mass, rather you would have full escape of mass. That is, all of these measures that we would take along these branches, they would have to converge to the zero measure. So before I go to the dramatic part of the talk, are there any questions? Okay, then, so if there's no questions, I'll go to the very nice dramatic part, which is that we disprove this conjecture. So this is joint work that I did with Erez Nesharim and with Steven Robertson. And here's our conjecture. Here's how we disprove it. We construct actually for every prime p that some theta p that it's going to depend on the characteristic P here that satisfies the following. So firstly, Theta is going to have 2 over P escape of mass exactly when P is odd. And when P is even, it will have 2/3 escape of mass exactly when P is even. So the case that P is odd is my work with Steven, and the case that P is equal to 2 is my work with Erez, and we have explicit constructions for all of these thetas. So what does this mean that it exhibits exactly this much escape of mass? This means that this lim inf here that I wrote out is going to be equal exactly to 2 over P for P odd and 2/3 when P is even. So this lim inf is not going to be 1, which is what you would want in the full escape of mass setting. But another thing that happens is that this is not, you wouldn't say that it's a strong counterexample, because if you were to just switch this lim int with the lim sup, then you would get 1 in both of these situations. So this, we call this maximal escape of mass of being 1, whereas the escape of mass is not full itself. So now let's talk about how we proved this, because we did not use continued fractions, nor did we use Hecke trees to prove it. Rather, we used something different, which is something that's called Henkel matrices and flats. Sorry, so now if you have a Henkel, so we define for a sequence of numbers in FQ, we're going to define the Henkel matrix starting at theta k of order m plus 1 to be the following matrix. So the first row is just theta k plus 1 up to theta k plus m plus m. The second row is just a shift by 1 of the first row, and then you just make this to be a square matrix. So these are going to be our major players here. And now we define the flat of theta to be the following two-dimensional array. So this array is going to be as follows. If you're above the main diagonal, then everything is going to be zeros. On the main diagonal, you're going to have 1s, and then below that, you're going to have, whenever m is equal to n mod 2, you're going to have zeros, and then otherwise, you're going to have the determinant of this Henkel matrix here. I will say that this definition looks kind of funny, because originally the thing that people were discussing is something called number walls, which is the rotation of flats by 45 degrees. But Erez and I decided to define these flats because they correspond better to the dynamics of the Hecke tree and the dynamics of PGL2 of the Laurent series times PGL2 of the completion at T of the rational functions. So that's the idea of it. So now let's see some pictures, since it's kind of hard to hold this definition in your head. So this, for example, is the flat of the Thue-Morse sequence, which this was our counterexample when you take P equals 2. So if we just look at this a little bit, what are some things that we can see here? So as I said, everything that's above the main diagonal is going to be zeros. And you see that this is constructed of a bunch of diamond-shaped windows. And this is one of the things that is going to be very important in our escape of mass. So let's talk about how we use these and these diamond-shaped windows to discuss this escape of mass of continued fraction expansions. So the theorem that we're going to use is a theorem by Kamei, Tamura, and Wen from 1997, which says the following. If you have some continued fraction, theta, and you're going to write the convergence, Pn over Qn, just to be this continued fraction when you cut it off after endpoints. Then we have that the flat at these coordinates. So I think that this should be opposite here. No, this is fine. So if you take the first column of the flat and the mth row, then this is going to be non-zero if and only if there exists some n such that the degree of Qn is equal to m. And as we know, these degrees of Qn are increasing. So we can just write an increasing sequence here, that of all of these indices where this is not going to be 0. And what does this give us? This gives us a different way to look at escape of mass by simply using these number walls and flats. So the idea is this: if you have some theta, which is going to be some quadratic irrational, look at t to the k theta, write it out in this form. Pretend for a moment that it doesn't have an initial part, because our specific continued fractions don't have one. And now we're going to let hkj be the jth non-zero coordinate in the kth column of f. So maybe I'll show you a picture. So here, for example, let's take a specific column. So I'm just going to try to draw this somehow. Thanks. Okay, so let's say I took this column here. So here I would have, this is the column that I'm taking. And then here I would get, for example, that this would be the first one, the second one, next one. So these are the points that I'm referring to, these HKJs, if this is the kth column. Okay, so now we have the theta is going to exhibit exactly C escape of mass if and only if for any n, if you look at the differences between these guys and you look at what is the maximum difference, that's going to be the maximum of all these differences minus this n, and you take the maximum on all of these, divided by the sum of these differences. So you could say this as the period of the column. And in our case, the columns are bound to be periodic because the continued fraction expansion here is periodic. So if and only if this is equal to C. So that's what is equivalent to the C escape of mass. Are there any questions until now?
Well, there was a question from K1 in chat.
Oh, sorry, yes.
It's still applicable.
Sorry.
The Lim-Sup statement. Is the Lim-Sup statement for all choices of theta or not?
No, no, it's not for all choices of theta. It's for one specific theta. We construct these explicitly. But this is a good question because we conjecture that it should be true for all thetas in the Lim-Sup case.
Okay.
Okay, so basically what we see here from this corollary is that the escape of mass of the continued fraction expansion, it would correspond to the proportion that these blocks, they take up in the entire period of the column. So now we are going to discuss zero blocks in these flats and some known results. So some known results about zero blocks in flats actually are the first ones. So firstly, if theta is quadratic irrational, then it's going to contain windows of unbounded size. And this was by Mathan and Teullie. Recall that earlier I said that Mathan and Teullie showed that the maximal AK, the maximal degree of AK that you will see in when you take the limit going to infinity in the periodic part is going to be infinity. And this is the exact interpretation of it if we go back to this corollary. So that's actually what they proved. And then some other known results are that, so this was what I said, that there is some escape of mass for these t to the k thetas, where theta is a quadratic irrational. And some other known results is that it's not necessarily obvious that a flat is going to have windows of unbounded size. And moreover, there are counterexamples of flats that they have zero windows of bounded size. This is a seminal, so first people to do this was a seminal result by Erez Nesharim in London. And then after that, there were some more examples found by Robertson and Robertson. And one can ask, why would you do this? So the entire reason why they studied these flats of these zero windows is because of the following. They are it turns out that a flat is going to have zero windows of unbounded size if and only if it satisfies the conclusion of the Theatic-Littlewood conjecture. And the Theatic-Littlewood conjecture says the following, that Theta is going to satisfy it if the infimum on all n's, which are going to be in f, which are polynomials of n times the t-adic norm of n times the distance of n theta from the polynomials is 0. If you don't like this t-adic norm, you could also view it like this. As the infimum of n times this guy here, n, the distance of nt to the k theta from the polynomials is going to be 0. And the way that that all of these results here, all these authors here, that they showed these, the reason why they showed these flats that they had 0 windows of bounded size was to find counterexamples to this conjecture, which, by the way, its real analog is currently, it's not clear if it's true or false yet. So now there's some of these results on 0 blocks and flats, and we are going to discuss these 0 blocks and flats, but in a different direction for escape of mass. So let's discuss our method of proof now. So for this proof, what we did was that we defined some tiling from a small set of tiles, there's some symbols, T, to matrices of order P by P over T. And then we have this tiling here. Now, next thing that we did was that we took the image of this tiling and then we defined a coding. This here is for the that's going to take this tiling here to matrices of order P by P or something larger than that in some of these cases over F2 to obtain some new matrix F. And then the last thing that we did was that we showed that this matrix F has the same structure as the flat, I wrote here building, I meant to say flat, of either the Thue-Morse sequence or the P-Cantor sequence, which these are our explicit counterexamples. And then we used symmetries and the self-similar structure of this tiling and of this coding to find these sequences that they exhibit this exact amount of escape of mass. That is, these sequences that they give us this lim infinite escape of mass. And then for the maximal escape of mass, we used, again, self-similarity to find sequences that they give us this maximal escape of mass at that lim sup. So now maybe I can write down what these sequences are. So when we take P equals 2, I said that we had some tiling. So what's a tiling? A tiling is something like this. You start with something, we start with some tile, and then after that you say that every time that you see this tile, you're going to take it to a bigger tile that looks slightly different. So this is an example for the Thue-Morse tiling that looks more or less like this, and this guy here would go to something that's larger, the same guy but larger. So it turns out that both the Thue-Morse sequence and the P-Cantor sequence, they're generated by tilings. And by the way, this is simply because they're quadratic irrationals, and therefore their coefficients are automatic. And this is a well-known theorem from automatic theory. So now I'll explain how we generate these. So for the P equals 2, this is the Thue-Morse sequence. The tiling that we use to generate our sequence of, this is going to be just of the coefficients theta n, is going to be every time that you see a 0, you take it to 0, 1. And every time that you see a 1, you take it to 1, 0. And this is going to define some sequence that is a quadratic irrational. And then for general P odd, we did something different, which was that we took, which is a little bit more complicated, but more or less what we did was that we took n to go to n times p choose 1, 0, and then after that we do n times p choose 2, and so on and so forth, 0, so on and so forth, until we get 0 to n times, I wrote it like this, n times p choose n, when n is going to be something that's going to be in 0 up to p minus 1. And of course, this is mod p. So these were our counter examples that we constructed in all of these characteristics. So now let's see some cool pictures. So the first one is, this is the tiling for the Thue-Morse sequence. So maybe I'll take a minute to look at this picture with you guys, and we'll see some properties here. So one of the properties that you may see is that we do indeed have these white windows, and not just that, these white windows, they have the same frames. That is, we see that we have this frame here is going to look a lot like this frame here. And not only do we have here red blush, pink blush, and yellow on all of these, if you look at the frame that's right outside of it, we have some type of teal, gray, green, and then these different shades of blue here. And this is for both of these. So this is actually a property of these flats, which is called the frame constraints. And that was how we were able to prove that in the end, the sequence that we generated indeed generates the flat of the Thue-Morse sequence. Not just that, you could see another thing here, which is if you choose to say that this shade of blue is 0 and this shade of blue is 1, and you see here 0, 1, 1, 0, 1, 0, 0, and this is actually the Thue-Morse sequence, but in these new symbols. And we see that we have some of these columns being periodic, like this one here, or this one here, and some of the rows being periodic, like this one here, or this one here. And these are some examples of the symmetries that we utilized in order to prove this escape of mass. Now, after you see this image here, so this was the tiling, then we coded it by taking this to certain things over F2. So we just changed these colors to just be black and white. And after changing it to be black and white, this is what we get. And based off some rule, then this is the coding that we'd get here. And then what happened was that these sequences that exhibit minimal escape of mass are actually exactly these guys here. They're in the middle of these squares. And why is that? Because the period of this column here is going to end right around. So if you were to start the period here, say, then this period would end here. And then the only part that you could have that you would have something that's proportionally large is going to be here. But in all of these, you would have this part that's proportionally large, but you might also have some extra things. So that was the idea here. And then for these ones, this would be something like this. This one, so if you would take these guys here, they would eventually exhibit the full escape of mass. So these are some of the pictures that we had for this. Now, let's see what happens for the P-Cantor sequence. So here we did something a little different for the P-Cantor sequence. Here we don't have the flat, rather we have the number wall, which is the rotated flat. And here, as you can see, again, you have a bunch of symmetries. That is, you see that you have something here that has a bunch of small squares, then something here that's red, that's an entire square of red, but then you have these funny blue lines. And then these ones here are a bunch of small squares. And these ones here look a lot like these ones. And these ones look like a rotation of these ones. But these ones are all red. The red, by the way, are the 0 windows. And then what we did after this is that anything that's going to be, and this is just a portion, but later on it gets bigger. But the idea here is that anything that's red, we would map it to just be white and it would be zeros. And anything that's of a different shade, we would map it to be black, and that would be like ones. And then we would ask, does this give off a similar structure as the building, or as the flat or the number wall of the 11 Cantor sequence? And that's how we prove this. And now that we've gotten, so these are some of the pictures that we had so far about this. Are there any questions?
So there's something I was confused about.
Yes.
When P was equal to 2, you constructed this Thue-Morse
Yes.
sequence, and the corresponding element is quadratic irrational, you're saying?
Yes. I mean, if you take the Laurent, so let's do this. So if you do this, you get some series, Theta n, and this is going to be an F2. And then now you can look at the quadratic irrational, which is going to be the sum of theta n t to the minus n. You can prove that this is going to be a quadratic irrational by using some of these, by using this tiling here.
Mm-hmm. So that's not different from the real case.
Yeah, it's different from the real case. In the real case, you don't have some construction like this.
Mm-hmm.
And this is the exact upshot here, that in this setting, you have a bunch of these types of constructions with automatic sequences, and you have this crystal theorem that says that if you have a quadratic irrational like this, then it has to be able to be constructed from some type of tiling like this, from a substitution tiling.
Mm-hmm.
And then we did the same exact thing for the odd case. Does that answer your question?
So you have a specific quadratic equation that
Yes.
satisfies?
Yes.
Okay, interesting.
Yes, and the same for this one. We have a specific quadratic equation that it satisfies.
Mm-hmm. Okay, thank you.
Okay, then, so now that we're towards the end, then we can discuss some questions that I have for you all. And the first one is, we proved that this conjecture by Paulin and Shapira is false. So the natural question is, what's the Hausdorff dimension or measure of the set of counterexamples to these? That, or I would say, to me, it seems like this condition that every sequence would exhibit full escape of mass is highly restrictive. So I would say, I would say that the small set would be the set of those, but this is just an intuition. I'm not completely sure of it. Next, we can also ask, is it true that every rational branch is going to have 0 as an accumulation measure, Or if you'd like to talk about it into these flats, and you can ask, is it true that you can always find some sequence that's going to have very, very large zeros, that they take up almost the entire proportion of the branch? So that's like saying that the maximal amount of escape of mass is full. So we believe that. Sorry?
I'm confused. So the conjecture. So is the conjecture about quadratic irrationals, or it's about every element of FQ?
Okay. Okay, it's about quadratic irrationals, but over FQ.
Okay, but it looks like it's a countable set.
It's not clear what it is. Like, you could say, so it's not clear what it is. I think that it should be relatively large because the condition is just very, very restrictive.
No, I'm confused. So you have I mean, how many quadratic irrationals? What's the Hausdorff dimension of all quadratic irrationals?
Okay, yeah, that's small. I'm not sure if Hausdorff dimension is maybe the correct notion to discuss here, but there should be some notion of how to discuss these, since these are small. Or you could say the periodic orbits are also small, but I'm not sure if this is the correct notion to discuss this, but let's say in a general term, what's the size in some way or form? Maybe the correct notion would be some type of density or something.
Okay, yeah. Well, it's if it's a countable set, then there's no make sense to talk about measure or dimension, but maybe asymptotic proportion of
maybe asymptotic proportion. I haven't thought about this too much, but I just think that understanding what's the size of the ones that always have full escape of mass versus those that have partial escape.
Okay. Thank you.
No problem. And then next up is, so we said that we do believe that this is going to be true, that every rational branch will have 0 as an accumulation measure, or if you'd like the idea of it in flats, so that you could find a sequence of columns in the flat that will have escape of mass that's complete. But we believe that that something stronger occurs, which is that almost every accumulation measure is a 0 measure. That is, for example, in the Thumor sequence or in the P-Cantor sequence, where we have these counterexamples of these sequences that they exhibit partial escape of mass, we think that these sequences are very sparse or rare in some term or form. And this almost every is also something that's kind of weirdly stated here. And it may have, and this may be a density zero set, for example. And one way that we've been thinking about studying these is by using Markov chains, because they seem to be a useful tool to prove this conjecture that for every quadratic irrational, almost every branch is going to have full escape of mass in this sense. And to do this, this also uses some conjectures on tilings, which this is on tilings of these quadratic irrationals, which is something else that is an open problem that would be cool to do as well. So now another thing that we can ask is here, I didn't say this earlier, but the original question that Hecke and Shapira asked, that was not for in the p-adic case, rather it was the s-adic case. That is, you take your prime polynomials, where you take these primes to be from some finite set of primes in this case, and then you could ask what happens. So in the real case, the result is that there's no escape of mass in the s-adic case, and you can ask, is this actually true when you take the s-adic case, but in the positive characteristic setting? So this is another thing. And recall that here we only talked about taking one prime polynomial, which is going to be t, but we could have taken more. And then we talked here about these rational branches, but they're by no means generic. They're even countable. And we can ask, what's the accumulation points of measures when you take them along, let's say, generic branches that are not necessarily rational? So this was conjectured by Paulin and Shapira that they should equidistribute, and that the rational branches are just weird ones that do not equidistribute, and that they have escape of mass. And one question that one thing that they mentioned was that they believe that it could be that having some escape of mass corresponds to being a rational branch. That is, every branch that's not rational is going to equidistribute. And now we can ask another question, which was, we talked about all of this in the PGL2 setting. This is something that I don't understand too well, but is an interesting question, which is what happens in the building of PGL3. That is, you could ask the same type of questions there, and how do these questions look like? How does this escape of mass look like? Can we talk about these flats there or number walls? And do these sequences take any part? And what about quadratic irrationals? This is probably the wrong thing to talk about in the PGL3 setting, but is there something else that's similar to this? So there's a lot of open questions here, and there's also some of them may be low-hanging fruit. So if anybody wants to try them, that's also really nice, and I would love to hear about this. So if there's no more questions from the audience, I'll say thank you very much, and I'll give you all a picture of me and one of my little helpers drawing an earlier version of this tiling over here.
Okay, that's great, especially the picture. Thank you, Noi, for a great talk. Any questions? Let's give a virtual round of applause or audio applause. Any questions? So I have two questions, maybe before I forget. First of all, I remember Steven was talking about his counterexamples to Littlewoods and
yes,
some technique that, well, so those number walls that you
yes,
rotated and called something else.
flats, yeah.
So, but did you? So I'm just want to understand logistics. Did you use some results from his paper, or it's completely independent?
We used some results from his paper in terms of, but just to construct this number wall, actually. So Steven and I, we used some of those results to construct the number wall in a different way. with Erez, we did not use those results from the number walls paper. Rather, we just constructed it explicitly, but we had two different constructions. The one that I did with Erez was constructing the flat through a tiling and a coding, and then using the frame constraints in a classical way to prove that this is indeed the flat of the Thue-Moore sequence. And with Steven, we did something else, which is that we proved a bunch of lemmas that number walls must satisfy, and we showed that if you start at the beginning with the sequence that you want, and then you apply these lemmas one after another, then you get something that is bound to be the number wall.
Okay. Okay, I see. And the second question, you mentioned the aesthetic case and the
Yes.
several different primes.
Yes.
So does it mean, so returning to the very first example, does it mean that you can take a quadratic irrational and multiply it by powers of 6 and say something?
Yeah. For example, you could do that, and then you could ask, could you say something there? So in the aesthetic case, of course, because the t-adic case is basically part of the aesthetic case. That is, I could have just taken pi's, all of them to be the same polynomial. Then I will have some escape of mass. Then I will have some of these branches that they have partial escape of mass. But then the question is, would this be indeed the generic part? And this is something that would this be the generic case? That is, if you take almost any one of these, would that be the case?
Okay. All right, I see. So so the result about powers of 6 just follows from, I'm just talking about the real case.
Oh, the real case. Okay, yeah. In the real case, that just follows. So they did it for aesthetics, which is that no matter you choose some set S, and then you'll just have equidistribution along all of the rational branches, and the result is actually stronger than that. That is, besides in some very niche case that you may have two branches, at most, that do not equidistribute. Every branch that you take, not just rational, will equidistribute. And there it's true if you take powers of 6 or whatever you want.
Okay, I see. Okay, thank you. Any other questions?
I have a quick question.
Yes.
So I think you mentioned in your theorem that the limb soup, in the case of this particular quadratic irrationals that you construct, the limb soup is 1, right?
Yes.
So is it plausible that the limb soup is always 1?
Yes, that's actually a conjecture that we have.
Okay, I didn't.
Yeah, that was one of our conjectures that I said at the end.
I see.
Not just that, I believe that it's not just going to be always 1. Rather, I believe that for every quadratic irrational, you will have that almost any sequence of k's that you take, you'll get 1, and that we just so happen to fall on some weird sequence.
I see. Okay.
Always, I suppose it would mean of upper density, of full upper density, for example, or something like that. I have a different interpretation of this almost always, which is that if you were to, so recall that we had this tiling that we did where you take this and you make it larger. But then what if instead of making it larger, you would take this image, let's do it like this. So you take this image here, and then you would just rescale it to be small again. Then you would talk about columns, but instead of talking about all of these, then you would just say, I want to take a bunch of columns here. And then now you could talk about almost always of when you take columns that are in some rescaled setting.
Okay.
Okay.
Other comments or questions?
Thank you.
Okay, if not, let's thank Noe again. This was great. And thanks to all of you for participation throughout the semester.